Hello, my dear students. Welcome to IK Sir Chemistry classes. Here we are in lecture number 9 on the chapter Symmetry and Group Theory. In this video, we will discuss the multiplication of symmetry operations. First of all, we will see what is multiplication of symmetry operations. When two or more symmetry operations are carried out on a molecule one after another, they give rise to a symmetry operation which is called the product of such combination of symmetry operations. It means if two or more symmetry operations are carried out on a molecule one after another, they give rise to another symmetry operation which is called the product of such combination of symmetry operations. And this process is called multiplication of symmetry operations. It is represented as follows. B into A is equal to C. Here A and B are two symmetry operations which are carried out on the molecule one after another. As a result, it gives rise to a symmetry operation C, which is called the product of symmetry operations A and B. Here, the symmetry operation A, which is written on the right hand side, is carried out first, followed by B. It means the symmetry operation which is written on the right hand side is carried out first, followed by the symmetry operation which is written on the left hand side, and C is the product of symmetry operations A and B. And this phenomenon, this process is called multiplication of symmetry operations. Now the question arises how to find out the product of two symmetry operations. Let us consider a general point with coordinates x1, y1, z1. On applying a certain symmetry operation A, this point shifts to a new position with coordinates x1, x2, y2, z2. Let us consider a general point within the molecule with coordinates x1, y1, z1. Then symmetry operation A is applied on the molecule. As a result, the position of this point shifts to a new position with coordinates x2, y2, z2. Then on applying another symmetry operation B, this point again shifts to the position with coordinates x3, y3, z3. Thus, the net effect of applying two symmetry operations A and B on the molecule successively. Two symmetry operations A and B are applied on the molecule successively, that is one after another, and its net result is the shift of point under consideration from x1, y1, z1 to x3, y3, z3. Now we look at a way to accomplish this net change in one step. Now we look at for a way which can bring about this change in one step. If symmetry operation C does so, if symmetry operation C shifts the position of point from x1, y1, z1 to x3, y3, z3 directly, then it is called the product of first two symmetry operations A and B as illustrated below. Here is a point within the molecule with coordinates x1, y1, z1. Symmetry operation A is applied on the molecule. As a result, the position of this point shifts to a new position with coordinates x2, y2, z2. Thereafter, another symmetry operation B is applied on the molecule, and finally, the position of point shifts to x3, y3, z3. First of all, symmetry operation A is applied on the molecule, followed by symmetry operation B, and the net result is shift of point within the molecule from x1, y1, z1 to x3, y3, z3. If the symmetry operation C can perform this change in one step, then AC is called the product of symmetry operations A and B. It can be represented as follows: A into B is equal to C. Here also, the symmetry operation A written on the right hand side is carried out first, followed by symmetry operation B, and the net effect, the net result of symmetry operations A and B can also be carried out by symmetry operation C. Here C is called the product of symmetry operations A and B. Now, multiplication table for C2V point group. H2O is the simplest molecule belonging to C2V point group, and it has been represented here. This is C2 Z axis. It is twofold axis of symmetry. H2O molecule has identity element of symmetry, twofold axis of symmetry, and two vertical planes of symmetry, sigma by z. It bisects the angle between two OH bonds. And there is another sigma xz. It is the molecular plane. Both these planes of symmetry contain the z-axis. That is the principal axis of symmetry, and hence these are vertical planes of symmetry, sigma v. Thus, the symmetry elements in H2O molecule are identity C2Z, sigma xz, and sigma by z. Four symmetry operations can be carried out on H2O molecule which belongs to C2V point group, and these symmetry operations are given here: C2Z, C22, that is identity, sigma xz, and sigma by z. These symmetry operations are the elements of C2V symmetry group, which is nothing but a mathematical group. We have already seen that four symmetry operations can be carried out on H2O molecule which belongs to C2V point group, and these are C2, C22, that is E, sigma xz, and sigma by z. These four symmetry operations can be multiplied together in 16 different ways, as given in the following multiplication table. The multiplication table for C2V point group is given here. It is the multiplication table for C2V point group, C2V symmetry group, which is a mathematical group, and its elements are symmetry operations, identity, C2Z, sigma xz and sigma yz, which have been written in vertical direction. These symmetry operations are also written on horizontal position also, E, C2Z, sigma xz and sigma yz. There are 16 positions in this multiplication table for C2V point group, and each position represents the product of two symmetry operations. Let us consider the product at position number 10. The product is sigma by z. It is obtained by multiplying sigma xz symmetry operation by C2z symmetry operation. Sigma xz multiplied by C2z and their product is sigma yz. Let us consider position number 8, whose entry is sigma xz. It is the product of two symmetry operations C2z and sigma yz. C2z from here and sigma yz from here. C2z multiplied by sigma yz is equal to sigma xz, and how this product is obtained will be discussed on the later slides. There is another position 15 whose entry is C2z. It is the product of symmetry operations. It is the product of symmetry operations sigma yz, which comes from here, and sigma xz, which comes from here. Sigma yz into sigma xz is equal to C2z. The products, the entries at positions 1, 2 and 3, 4 can be obtained as follows. E multiplied by E is equal to E. E multiplied by C2Z is equal to C2Z. It must be remembered that the identity element of symmetry commutes with any other element of the mathematical group and leaves them unchanged. E multiplied by E is equal to E. E multiplied by C2Z is equal to C2Z. E multiplied by sigma xz is equal to sigma xz, and E multiplied by sigma yz is nothing but sigma yz. These are the products at positions 1, 2, 3 and 4. Similarly, position number 5, C2Z multiplied by E is equal to C2Z. Sigma xz multiplied by E is equal to sigma xz, and sigma yz multiplied by E is equal to sigma yz. Let us illustrate the product of positions diagrammatically. The products written at various positions can be derived as follows. We have already seen at positions 1 to 4, E into E is equal to E, E into C2Z is equal to C2Z, E into sigma xz is equal to sigma xz, E into sigma yz is equal to sigma yz. And at positions 5, 9 and 10, and 5, 9 and 13, which are in the vertical position, C2Z into E is equal to C2Z, sigma xz into E is equal to sigma xz, and sigma yz into E is equal to sigma yz. The identity element of a mathematical group commutes with all other elements of the group and leaves them unchanged. Let us find out the product written as position number 7. C2Z into sigma xz. C2Z into sigma xz. Here, sigma xz operation written on the right hand side is carried out first. If this H2O molecule is reflected through the molecular plane, there will be no change in the orientation. Then we applied C2Z operation, which is written on the left hand side, and if this H2O molecule is rotated about Z axis by 180 degree, this red colored hydrogen atom will come to this position and this blue colored hydrogen atom will come to this position, and the net result is given here, and this net change of two symmetry operations sigma xz and C2z can be carried out by only one symmetry operation sigma yz. If this H2O molecule is reflected through yz plane, its reflection will be obtained here and its reflection will be obtained here, and the net result is given here. Thus, the product of sigma xz and C2z symmetry operations is nothing but sigma yz. Let us now consider the multiplication of symmetry operations at position number 8, C2z into sigma yz. The sigma yz operation written on the right hand side is carried out first. H2O molecule is reflected through yz plane and the new orientation obtained is given here. Its image will be obtained here, red colored, and blue colored hydrogen atom will shift to this position. And then C2Z operation is carried out, which has been written on the left hand side. If this H2O molecule is rotated about Z axis by 180 degree, this hydrogen atom, red color, will come to this position and blue color hydrogen atom will come to this position, and the new orientation obtained is given here, which can be obtained by applying sigma xz operation on H2O molecule. If this H2O molecule is reflected through xz plane, that is molecular plane, no change in orientation will take place. It means the product of sigma yz and C2z symmetry operations is nothing but sigma xz. It is the product of symmetry operations sigma yz and C2z. Let us consider the product at position number 12, sigma xz multiplied by sigma yz. Here also the symmetry operation written on the right hand side is carried out first, followed by symmetry operation sigma xz written on the right hand side, and this net result, if the H2O molecule is reflected through this plane, yz plane, new orientation obtained will be here, its image will be formed here and its image will be formed here, and if this H2O molecule is reflected through molecular plane, no change in orientation will take place, and this molecule, this orientation of H2O molecule can be obtained by applying C2Z operation. If H2O molecule is rotated about Z axis by 180 degree, this hydrogen atom will come to this position and red colored hydrogen atom will come to this position. It means the product of sigma yz and sigma xz symmetry operations is C2Z. It is obvious that each row and each column of the multiplication table of C2V point group contains the same 4 symmetry operations. Each row and each column of the multiplication table of C2B point group contains the same four symmetry operations C2Z, C22, that is E, sigma xz and sigma yz, but in different order. Similarly, the products at other positions can be derived. At position number 6, C2Z into C2Z and it is equal to E. At position 10, sigma xz into sigma yz and it is equal to C2Z. At position 11, sigma xz and it is equal to E. At position 14, sigma yz into C2Z is equal to sigma xz. At position 15, sigma yz into sigma xz is equal to C2Z. These products can be obtained in similar manner as discussed earlier. And at position number 16, sigma yz is equal to E. Now the time for self-assessment. Prove that C2V point group is a mathematical group. Here is the answer. The symmetry operations of C2V point group obey all the four rules of a mathematical group. The symmetry operations of C2V point group obey all the four rules of mathematical group, such as law of identity. The identity operation E commutes with all other elements, commutes with all other symmetry operations. Here it is redundant more than sufficient. Commutes, the identity operation E commutes with all other symmetry operations of C2B point group and leaves them unchanged, such as E into C2Z is equal to C2Z into E and it is equal to C2Z. E into sigma xz is equal to sigma xz into E and it is equal to sigma xz. E into sigma yz is equal to sigma yz into E and it is equal to sigma yz. The identity operation of C2V point group commutes with all other symmetry operations and leaves them unchanged. The another law is law of closure. The product of any two symmetry operations and the square of each symmetry operation of C2V point group belongs to the same point group, such as sigma yz multiplied by sigma xz is equal to C2z, which belongs to C2V point group. C2z multiplied by sigma xz is equal to sigma yz, which again belongs to C2V point group. At the same time, the square of each symmetry operation also belongs to the same point group. C22 is equal to E, sigma xz2 is equal to E and sigma yz2 is equal to E. The product of any two symmetry operations as well as the square of each symmetry operation of C2B point group belongs to the same point group and thus the law of closure is obeyed. The third law is law of inverse. Each symmetry operation of C2B point group is the inverse of itself because each symmetry operation when multiplied by itself produces identity operation. Sigma xz into sigma xz is equal to E. Sigma yz multiplied by sigma yz is equal to E and C2z into C2z is equal to E. Each symmetry operation of C2B point group is inverse of itself because when each symmetry operation is multiplied by itself, the net result is equal to E. And the fourth law of a mathematical group is law of association. The law of association holds good among the symmetry operations of C2B point group. For example, sigma yz, sigma xz, and C2z symmetry operations can be multiplied in two different ways, giving rise to the same result. In the first method, A, first of all, sigma yz and sigma xz are multiplied, whose result is C2z, and this C2z is then multiplied by this C2z, and the net result is E. In another way, B, first of all, sigma xz and C2z are multiplied, whose result is sigma yz, and this sigma yz is multiplied by this symmetry operation. Sigma yz into sigma yz is equal to E. Thus, all the four rules for a mathematical group are fulfilled, are satisfied, are obeyed by the symmetry operations of C2B point group, and therefore C2B point group is a mathematical group. There is another time for self-assessment. Prove that C2B point group is an abelian group. We have already seen in previous video that the group, the mathematical group in which all the elements commute with one another is called an abelian group. Here is the answer. The symmetry operations of C2B point group are C2, C22, sigma xz, and sigma yz. These symmetry operations of C2B point group commute with one another as illustrated below. Sigma yz into sigma xz is equal to C2z, and sigma xz into sigma yz is also equal to C2z. Thus, these two symmetry operations commute with each other. C2z into sigma yz equals to sigma xz, and sigma yz into C2z is again equal to sigma xz. It means C2z and sigma yz symmetry operations commute with each other. C2z into sigma xz is equal to sigma yz, and sigma xz into C2z is again equal to sigma yz. Thus, C2z and sigma xz symmetry operations commute with each other. These products can be obtained from the multiplication table of C2B point group, and therefore C2B point group is an abelian group because all its symmetry operations commute with one another. Thank you for watching the video with concentration. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.